Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic, we're going to give the definition of linear maps and linear operators. So in this topic, we will define a linear map. We will also define a linear operator. We will understand what this implies. We will look at a test for linearity and how to determine when a map is not linear. We will look at some examples. We will then see that all finite dimensional linear maps can be represented by matrices. And then we will learn that the image of a linear map can be calculated performing a matrix vector multiplication. Now, recall there are two operations we can perform on vectors: scalar multiplication and vector addition. A map A mapping a vector space U onto a vector space V is said to be a linear map if it preserves scalar multiplication and vector addition. So for example, if I have a signal and amplify it by alpha and then map that under A, that is the same as mapping the original signal under A and then amplifying that result. Similarly, the response to adding the sum of two vectors is equal to the response of each of the vectors added together. That is to say, the response to a linear combination of inputs is equal to that same linear combination of the responses to the individual inputs. Now, visually, we can approach this in two ways. So on the left-hand side, we have an input vector x, and we can either multiply x first by alpha and then put it through the linear map and determine the response, or we can put the signal x through the linear map and then multiply the result. These two should give the exact same output. On the right-hand side, we start in the top left with a vector in the vector space U. We can either go to the right and apply the mapping A, which gives us a vector in V. In the vector space V, we can now multiply that result by alpha. That is going to be the same as if we started in the top left, first multiplied U by alpha to get another vector in U, and only then apply A to get the result in the vector space V. These two should be equal. The same for vector addition. We can either sum the two vectors and then apply the linear map, or we can apply the linear map to both A and X and Y and then sum their outputs. These should be the same. So on the right-hand side, once again, given U and V as vectors in the vector space U, we can either immediately go into the vector space V by applying the linear map and then adding the results, or we can stay in U, add the two vectors together, and then apply the linear map to that sum. These must always be the same. Now, here's a nice little theorem. If A mapping a vector space U onto a vector space V is linear, then A applied to the zero vector of U equals the zero vector of V. That is, for a linear map, the zero vector in U must be mapped to the zero vector in V. Proof. Well, let U be any vector in U. Now, we know that 0 times that vector U is the zero vector in the vector space U. Thus, if we were to apply A to the 0 vector of the vector space U, that is the same as applying A to 0 times U. But if A is linear, then we can take the 0 out of the application, and so that needs to be equal to 0 times the image of U under A. But wait a second, the image of U under A is a vector in V. So 0 times a vector in V is the 0 vector in the vector space V. Here's another nice result. If A mapping U onto V is a linear map, then A maps lines in U onto lines or a single point in V. Proof. Well, a line in U is anything of the form one vector U1 plus all scalar multiples of a second vector U2. Now this is in the vector space U. Therefore, if we were to apply a linear map, then this linear map applied to U1 plus alpha times U2 is equal to the linear map applied to U1 plus alpha times the linear map applied to U2. Now, in the odd case that the linear map applied to U2 is the 0 vector in the vector space V, then the image of U1 plus alpha times U2 is simply the image of U1. All right. However, if A applied to U2 is not the 0 vector in V, then A applied to U1 plus alpha times A applied to U2 is just a vector in V plus all scalar multiples of another vector in V, which is once again a line in the vector space V. There's a second nice result which we will not prove, but it says that a linear map maps any circle or ellipse that is centered at the origin to another circle or ellipse or line segment that passes through the origin. Now, just one quick definition. A map that is linear, that maps a vector space onto itself, is said to be a linear operator if the domain and codomain are the same vector space. Another definition. Any two linear maps, A and B, mapping a vector space U onto V, we will say that those two linear maps are equal if and only if A applied to U is equal to B applied to U for all U in the vector space U. Now, you can show that a map A that takes a vector space U and maps it to a vector space V is linear by showing either that, first of all, A times A applied to alpha U is equal to alpha times A applied to U for all U in the vector space U and for all alpha in the field. That field can either be the real numbers or the complex numbers. Also, A applied to the sum of two vectors in U is always equal to the sum of A applied to each of them for all vectors U1 and U2 in the vector space U. Alternatively, if you can just show that A applied to this linear combination of U1 and U2 is equal to that same linear combination of A applied to each of U1 and U2, And you'd have to show that this is true for all u1 and u2 in the vector space U and for all alpha and beta in the field. Now, it's important. You only have to show one of these two requirements. If the two conditions in requirement 1 are true, then requirement 2 is true, and if the condition in requirement 2 is true, then both conditions in requirement 1 are true. Now, to show that a mapping A that takes a vector space U onto another vector space V is not a linear map, it is actually only necessary to show any one of either A applied to the 0 vector is not of U is not equal to the 0 vector of V. A applied to alpha times U is not equal to alpha times A applied to U for one U within the vector space U and for one alpha in the field. Or you can show that there are two vectors u1 and u2 such that A applied to the sum of u1 and u2 is not equal to the sum of A applied to each of them. And again, you only have to find two vectors in all of U, and if this one statement is not true for those two vectors, then the map is not linear. Let's look at some examples. Here I have a mapping that takes a two-dimensional vector that has entries u1 and u2 and maps it to R3 by letting u1 and u2 be the coefficients of a linear combination of these two vectors 0.5, 1.2, and 0.9, and the second vector being 0.8, 2.3, 1.7. All right, let's try to see if this is linear. Now, if we apply alpha to, or the mapping A onto alpha times U plus beta times U2, well, that's the same as multiplying the first vector by alpha times the first entry of U1 plus beta times the first entry of U2, plus alpha times the second entry of U1 plus beta times the second entry of U2 times that second vector. But wait a second, with the properties of scalar multiplication and vector addition, I can expand this as follows and then collect on alpha and beta. All right, but now if we take a look at the first one, wait a second, that first is just alpha times A applied to U1, and the second is beta times A applied to the vector U2. Okay, so this mapping A is linear. Let B be the mapping that takes a vector in R4 into R2 be defined as follows. B takes this four-dimensional vector and maps it to U1 times the first vector plus U2 times another vector plus U3 times a third vector plus U4 times a fourth vector plus the fifth vector 8.9, 1.2. So is this linear? Well, this one's really easy to show that it is not linear. After all, if we apply this mapping B to the 0 vector, we just get 0 times each of the first four vectors plus that last vector. And so therefore, the image of the 0 vector under this map is 9.8, 1.2. Well, this is not equal to the 0 vector in R2, so this particular B is not linear. Now, let C be this mapping from R3 to R2 defined as C applied to this three-dimensional vector equaling the vector u1 minus u2 and u2 minus u3. Is this a linear mapping? Well, looking closely at this, we see that C is just u1 times a vector, 1, 0, plus u2 times the vector negative 1, 1, plus u3 times the vector 0, negative 1. Well, using the same approach we saw 2 slides ago for A, we can also use this approach to show that C, too, is linear. Now, let D be the mapping from R4 to R4 defined as the following mapping. Once again, we see that D can be rewritten as a linear combination of 4 vectors in R4, where the entries of U, the vector that we're mapping, become the coefficients of those 4 vectors. Well, therefore, using the same approach as we just saw for that mapping A and the same approach we would have used for C, we can also show that D is linear. Now, here's E. E maps R2 onto R2, where the vector u1, u2 is mapped onto cos of u1 minus 1 and sine of u2. Now, E applied to the 0 vector is still cos of 0 minus 1 and sine of 0. But that's just 1 minus 1 and 0, and so, well, we can't show that this is not linear that easily. However, notice that this mapping E applied to 2 times the vector 2, 2 is equal to E applied to the vector 2, 2. That's equal to cos of 2 minus 1 and sine of 2. However, 2 times E applied to the vector 1, 1, if you expand it out, it becomes 2 times cos of 1 minus 2 and 2 times sine of 1. Are these vectors the same? Well, no, they're not, because 2 times sine of 1 is approximately 1.6829, and sine of 2 is a value between negative 1 and 1. Consequently, E is not linear. Now, here's a cute one. Is a linear polynomial linear? More specifically, let F be the mapping from R1 onto R1, where F takes a one-dimensional vector u that has one entry u1, and that is mapped onto the one-dimensional vector with the entry 2u plus 1. So, is that linear? Well, unfortunately, it isn't, because F applied to the 0 vector in R1 is the vector containing the entry 1, and that is not equal to the 0 vector in R1. Therefore, a linear polynomial is not a linear mapping. Here's one that's slightly different. Let's map R2 onto R2, where G is defined as cubing each of the entries. Once again, we see that 0 is mapped to 0, yet G applied to 1, 1 is just the vector 1, 1, whereas G applied to the vector 2, 2 is the vector 2 cubed, or 8, 8. But twice G of 1, 1 is equal to twice the vector 1, 1, which is equal to 2, 2. And that is not equal to the vector 8, 8, which is the image of G of 2 times the vector 1, 1 under the mapping G. Thus, this mapping G is not linear. Now, a general observation. For finite dimensional vector spaces, it seems that a mapping, A taking a vector space f to the n, mapping it to f to the m, it is linear if and only if A is defined as the entries of U becoming the coefficients of a linear combination of n vectors from f to the m. That is, there exists n vectors in f to the m such that A applied to U is just this linear combination of the vectors v1 through vn, where the coefficients are the entries of the vector u. Now, can we go the other way? Given a linear map, A mapping f to the n to f to the m, does this linear map necessarily define a linear combination of n vectors in f to the m with the coefficients coming from the vector u in f to the n? That is, if A is a linear map, do there exist n vectors v1 through vn such that we can write A applied to the vector u as u1 times the vector v1 plus u2 times the vector v2 plus all the way to un times the vector vn? Well, here's the solution. In the domain f to the n, let e1 through en cap be the canonical basis vectors. So e1 has zeros everywhere except in the first location. e2 cap has zeros everywhere except in the second location where there's a 1, and so on and so forth. Thus, we will define the vector vk in the codomain as A applied to the vector, the canonical basis vector e cap k. So, therefore, given any vector u in f to the n, we see that A applied to u, well, u is just u1 times the first basis vector plus u2 times the second basis vector, all the way up to the last entry of u times the last canonical basis vector. But wait a second. Now we are applying the linear operator, or mapping, to a linear combination of vectors. So this is just equal to this linear combination. Well, if we define A applied to the kth canonical basis vector e cap k, then we see that yes, A applied to u is indeed a linear combination of a collection of n vectors in the codomain f to the m, and the coefficients of this linear combination are given by the vector u. Now, given a linear map, A mapping f to the n to f to the m, we will represent A as an m by n matrix. So these n vectors will form the columns of this m by n matrix. Each of these columns is m-dimensional, the dimension of the codomain, or the mapping 2 of the vector in f to the n. So each column A sub k is in f to the m, and we will describe A applied to u as the matrix vector multiplication. So now from here on in, rather than saying we are applying a linear operator A onto the matrix U, we will just describe this as a matrix vector multiplication. Now, one way to look at this is, of course, the way we've already done so. We can consider A times U as the linear combination of the first entry of U times the first column of A plus the second entry of U times the second column of A, and so on and so forth. Now, it's also possible to think of matrix vector multiplication as follows. Here we see the M by N matrix A followed by the n-dimensional vector U. And of course, this is a column. So therefore, we want to determine the values of the image of U, the first entry of which is V1, then V2, then V3, all the way up to Vm, as after all, we are mapping from f to the n to f to the m. Well, to get the first entry, we consider the first row of A and the vector U, and we calculate the pairwise products and sum them up. So A11 times U1 plus A12 times U2 plus A13 times U3 plus A14 times U4 plus so on and so forth up until we add A1n times UN. And that will give us the entry in the image V1. Next, we take the second row, and once again, we multiply the first entry of the row with the first entry of U, plus the second entry of the row times the second entry of U, and so on and so forth. And this will give us the second entry in the image. We can do so for the third entry of the image. Again, element-wise multiplication of the third row times the corresponding entries of the vector U, and so on and so forth until we get to the very last row. And to calculate the last entry Vm, we once again multiply the corresponding pairs of elements, am1 times u1 plus am2 times u2 plus so on and so forth to get the last entry v sub m. Recall that the first example of a linear map was this linear map that mapped R2 to R3. The corresponding matrix representation is exactly that matrix that has the two column vectors 0.5, 1.2, and 0.9, and 0.8, 2.3, 1.7 as the two columns of that matrix. Consequently, if you had a vector u in the domain, so in this case 0.3, negative 0.1, then to find the image, we would calculate the matrix A times the vector U. Now, it doesn't matter whether or not you think of this as 0.3 times the first column minus 0.1 times the second column, or if you were to calculate each of the entries of the image separately. So 0.5 times 0.3 plus 0.8 times negative 0.1, giving 0.07. Then 1.2 times 0.3 plus 2.3 times negative 0.1, that would give 0.13. And finally, 0.9 times 0.3 plus 0.7 times negative 0.1, and that gives us the value 0.1. The second linear map we had mapped R3 to R2. Now, with a little bit of work, you should be able to see that the matrix representation of this linear map is this matrix here. So again, there is no U1 in the second entry, so we have a positive 1 and a 0 for the first column. U2 has a negative 1 coefficient in the first entry and a positive 1 entry in the second one, so the second column becomes negative 1, 1. And finally, from the third, we can deduce that the third column should be 0, negative 1. Taking a vector such as 0.5, 0.2, negative 0.7 in the domain, if we want to find the vector in the range, or codomain, we will multiply C by that vector U. So again, whether or not we have this calculated as 0.5 times the vector 1, 0 plus 0.2 times the vector negative 1, 1 minus 0.7 times the vector 0, negative 1, or if we calculate each of the entries of the image separately, so 1 times 0.5 minus 1 times 0.2 plus 0 times negative 0.7, yielding the value 0.3. Next, taking the second row of C times the vector element-wise multiplied by the vector U gives us 0 times 0.5 plus 1 times 0.2 minus 1 times minus 0.7, yielding positive 0.9. The third and last linear map we just saw was the linear map D mapping R4 to R4. Now, D is a linear operator as the domain and the codomain are the same. Now, it doesn't matter if you call it, you can call a linear operator a linear map as well. However, a linear operator is specifically a mapping that takes a vector space into itself. So every linear operator is a linear map, but not every linear map is a linear operator. Anyway, here we see the result of the linear map D. Once again, with a little bit of work, you can tease out the coefficients of the matrix D. Consequently, if you had the vector, the four-dimensional vector 0.2, negative 0.3, 0.1, 0.4, and you wanted to find the image of this under the mapping D, once again, you could think of this either as 0.2 times the first column minus 0.3 times the second column plus 0.1 times the third column plus 0.4 times the fourth column, or once again, to get the first entry in the result, you multiply element-wise the first row of D times the corresponding entries of U, adding them together. Then the second row of D times each entry multiplied by the corresponding entry in U, then all added, and so on and so forth, to finally get the image of U under this linear map D. Following this topic, you now understand the definition of linearity for mappings between two vector spaces. You also know the test for linearity, and you know how to show a mapping is not linear. You know that the zero vector is always mapped onto the zero vector by a linear map, and we also saw that lines in the domain are mapped to either a point or a line in the codomain. We observed a number of examples, and we now know that a finite dimensional linear map can always be represented by a matrix. We also saw how to find those matrices. And you now also understand how to perform a matrix vector multiplication in order to find the image of a vector in the domain and to find its image in the codomain. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!